Now we're going to take a look at our voltage divider biasing network. And as we're going to see, this is going to fix the two shortcomings that we had with our single base resistor biasing scheme from the previous videos. The basic circuit we're going to use is shown here. So there's a couple differences and a couple similarities compared to our single base resistor scheme. So first of all, let me explicitly point out that this V sub S over here is now our AC source. So we're no longer explicitly drawing the voltage source, we just have it at a point. We still have our coupling capacitor CC, which is blocking DC signals while allowing AC signals to go through. We still have our RC connected to our VCC, so all of that is the same, but we have three new resistors. So we have, instead of just one resistor connected to the base, we now have two resistors, R1 and R2, connected to the base. One is going up to VCC like with our single base resistor, but now we've added another resistor R2 which is connected to ground. We've also added an emitter resistor R sub E, which we're going to see is going to help us stabilize our Q point against variations in beta. In order to analyze this circuit a little easier, what we're going to want to do is to reduce our base circuit by using Thevenin equivalent. So we want to reduce, and so we're just going to consider again the DC part for now. So we're going to reduce our base circuit with our Thevenin equivalent. And so again, just considering our DC. So in doing this, what we're going to assume is we're going to assume that our ICQ, our Q point, our collector current at the Q point is relatively small compared to the current coming through this voltage divider network. And keep in mind, of course, our base current is going to be small, but that's not necessarily true of the current coming through our R1 and R2. So what we can do then is we can sort of neglect that side, and we can say we have something that looks like this. So we have VCC, and then our two resistors, R1 and R2, R1, R2, and what we're interested in is sort of our input voltage at the base, which we can define as the voltage between this point and ground. So we have some VB that looks like this, and so of course this is VCC up here, and so let me just explicitly say we're assuming our IC is negligible, and so that's our ICQ. Okay. So we can sort of rearrange this. Again, I know it's maybe a little different seeing our circuits without explicit voltage sources. So if I redraw this, I think you're going to feel a little more comfortable finding our Thevenin equivalent values from this. So we can have some voltage source VCC, some resistor R1, R2, something that looks like this, R1, R2, and then our output is defined as across R2 because this is our ground here. So this is going to be our output voltage VB, and this is our voltage VC. So hopefully now that becomes relatively straightforward to find our Thevenin parameters. So our Thevenin voltage, remember, is our open circuit voltage. So if our VB is our VB voltage right here, if those terminals are open as they are for the circuit drawn above, we can say V Thevenin is just going to be the voltage across our 2 ohm resistor. So using voltage division, we can say that's VCC times R2 over R1 plus R2. And then of course for R Thevenin, we have several ways we can find that. The easiest perhaps is to deactivate our voltage source by shorting it, and then find the equivalent resistance looking in at our output terminals. Doing that, we can see we just have R1 in parallel with R2. Okay, so now we were able to sort of reduce that, but how do we come back and adjust our initial circuit? Well, it turns out what we can do, and again, we're just considering our DC analysis, is we're going to put our BJT in here. So we have something like this, and again, we've not really done anything to our collector resistor or our emitter resistor, but now we said looking off of the base, instead of having those two resistors and some voltage VCC, we now have one Thevenin voltage and one Thevenin resistance. So we get something that looks like this. So we have VCC RC, RE, and this is our R Thevenin, and this is our V Thevenin. And of course, we can label all of our standard values. So we have our collector current at the quiescent point, ICQ. We have some emitter quiescent current, IEQ, some base quiescent current, IBQ, and some collector emitter voltage, VCEQ. And so in the next video, what we're going to do is come back and analyze this circuit, and we're going to get some equations that describe its operation. We're going to see how it improves upon that single base resistor scheme, and then in a following video, we're going to work an example to get some practice.